Hello everyone, welcome back to part 3 of chapter 7. In this video we want to spend our time working on a few example problems that involve this idea behind work and changes in kinetic energy. But before we do that, as promised in a previous video, we also want to explore the means in which we are evaluating this cross product, because this method only really works if we have knowledge about the magnitude and the angle that exists between the two vectors. And so if I have a force vector and a displacement vector and an angle that exists between them, then I can plug all that information in, evaluate the work, no problem. But what if I had these force and displacement vectors provided in a different way? In other words, what if the force and the displacement vectors were described using component values? And these force and displacement vectors are 3D vectors. So our force vector could be three-dimensional, as could our displacement vector. And I'm just throwing in random values for each of these. So we'll say that our force vector has XYZ components as shown, and our displacement vector has XYZ components as shown. And we'd like to know how much work is done by this force as we displace over that displacement vector. And our means of evaluating says if you know the magnitude and angle, you can do that. Well, it's not that difficult for us to find the magnitude of these two vectors. All we have to do is take the square root of the sum of the squares, and we get the magnitude of each of those vectors. Well, all right, let's take a moment and plug all that information in. Get my calculator app out here. We have 4 squared plus 3 squared plus -5 squared, which is going to be positive. And that all comes out to the square root of 50, which is approximately 7.1 newtons. And then if we do the same thing for our displacement vector, we have -1 squared is 1. 6 squared and 7 squared. That comes out to be the square root of 86, which is approximately 9.27 meters. So we've got the first two pieces, but I don't know what the angle is between these two vectors. These vectors are pointing out in 3D space somewhere. I have no idea what the angle is between them, and if I don't know that, then I can't complete the evaluation of the work that's being done. There is a way that we can get around this, though. When it comes to the dot product, if you'll remember in a previous video, I said that only the force or component of force in the direction of displacement will do work. Okay. Well, our displacement vector has multiple components, XYZ, and our force has components, XYZ. If we were to take the dot product approach and apply it to every conceivable combination of the components, So in other words, there would be 9 different possible combinations. We'll take a moment and write all these out. And we have the FZ component combinations. Okay, so these are the 9 possible combinations that we could see of force components and displacement components. Remember, back in chapter 3, components of vectors are themselves vectors. They just happen to exist in one given axis. But this is actually very helpful to us because now if we attempt to take the dot product of every one of these combinations, dot products produce scalar quantities that can then be added together. And every one of these dot products is going to contain a cosine relationship between the angles of each of these components. And this is what's going to save us, because for every one of these components, we either have x, y, or z directions. In the case of 2 x components, the angle relationship between those 2 components is either going to be 0 or 180 degrees. So for cosine, 0 or 180 degrees, we either get plus or minus 1. What we need to do is we need to plug in the values of the x components of force and displacement. Our method for evaluating the dot product says we need to use the magnitudes of each. Well, the magnitude of the x component of force is 4. The magnitude of the x component of d is 1. And then we need the cosine of the angle that exists between them. Well, we have one component that is pointing in the positive x direction. We have another component that is pointing in the negative x direction. That is a cosine of 180, which is going to give us a minus sign again, or we get just -4. Now, this method of evaluating can actually be done a lot quicker and a lot easier if we just ignore this last portion. Because anytime we take the dot product between 2 components that lie on the same axes, our only choices are going to be plus or minus 1. And if we notice here, if we had just taken and multiplied the actual values of our components, we would achieve the same outcome of -4. And that just makes our life a whole lot easier because we can do this quicker. Now, for the next one in line, we have the x component of our force. We have the y component of our displacement, but the cosine relationship between something that points along the x direction and something that points along the y direction is 90 degrees. That's going to result in a 0. And this goes back to our concept statement up here that says that only force or component of force in the direction of displacement will do work. Well, that means that only the x component of force will do work along the x direction of displacement. And we should only expect the y component of force to do work along the y component of displacement. And we should only expect the z component of force to do work along the z component of our displacement. And so, correspondingly, only these combinations, of the dot products are actually going to produce anything, because all of the other combinations have components that lie in different axes. Each of these other situations is going to result in a cosine 90-degree relationship, and we're not going to get any contribution from those. And so it's just everything along the diagonal here that's actually going to contribute. And so this means that we can evaluate the work done by this three-dimensional force along a three-dimensional displacement by just taking the product of all of the components. Now, these, keep in mind, are component values. These are not differential statements. But this will tell us what the work done by the force is. And as we said, we're going to use the signs of those numbers, because we'll end up getting the same outcome as what the cosine relationship does. We had 4 and -1, which is -4. That component of force is actually doing negative work as we displace. We have 3 and 6, which is a positive 18. So this component of force is doing a positive amount of work. And then we have a -5 and a 7, which is a -35. Do -35. For a grand total of, let's see, 35 and 4. It's -39 plus 18 makes for a -21 joules worth of work that has been done by that force. And so there's our answer. We now know how much work was done by that force over that displacement. We can use this equation as a general solution for any combination of force components and displacement components. In this case, it's set up for a three-dimensional system of vectors, but we could just as easily use this for a 2D system. Now, for a 2D system, you would only have like X and Y components, but that would just mean that you would throw out the last term where you have 0 components in the Z direction. But we'll keep that as a general expression there. But now I'm curious, the fact that we weren't able to use this original expression to evaluate kind of has me irked, and I'd like to know what that angle is between these two vectors. And it's kind of difficult to draw 3D on a 2D surface, so I'm not even going to try. But if you can imagine these two vectors just kind of pointing out there in 3D space, and you want to measure the angle that exists between them. Well, how are we going to do that? Well, we can actually do it quite easily now, because we've just found out how much work has been done. And even though we've used the component form to evaluate that work, now that we know how much work has been done, we can plug that value in along with the magnitudes of the force and displacement, which we solved a few minutes back. We have 7.1, 9.27, cosine of theta. Well, theta is the only thing that we don't know now. We have -21 over 7.1, 9.27 equals cosine theta. I'm going to combine all of those numerical terms before I do my inverse cosine. 21, 7.1, and 9.27. Oops, there's supposed to be a bracket there. This gives a negative 0.32. So from there, the inverse cosine of the negative 0.32 will be our theta value. So inverse, we need inverse cosine of negative 0.32 makes for about 108.7 degrees. So that's how much of an angle we have between these two vectors. Now I don't know which is which, but if we want to let that be the force vector and that's the displacement vector, obviously this doesn't look like 108 degrees, but back with our discussions on evaluating work, remember we said that if our theta value exceeds 90 degrees, cosine becomes a negative quantity in its evaluation. And so it should make sense to us that the overall work done by this force through that displacement is a negative amount. All right, so there's two different ways that we can evaluate the work that is being done in a system of forces. We have the magnitude angle approach, or we can use the component method. Which one you use depends on how the material is presented. Obviously, if you already know the magnitude and angle, you should go with the first equation. If you don't have information about the angle, then using the component form is just as good. Okay, well, when it comes to all of this talk about work and energy, we said that we were going to start using this because eventually we were going to run into cases where the forces in the system were going to be variable. If we have a variable force, how does that affect things like the work that is being done? The two expressions that we have up here, these are means in which we can evaluate the work that has been done, but look at how we have to evaluate the work. In the first term, we have to use the magnitude of the force. But what is the magnitude of a changing value? If your force is constantly changing, what is its magnitude? And that doesn't really make sense. Well, the magnitude of the force would have to be measured at some specific moment or some specific location. And this was why back in the first video for this chapter, we said that force could vary based on a number of different possible variables. And if we want the magnitude of that force, then we're going to have to pick a specific place or time to evaluate that. But then if the force is changing as time goes by or as displacement goes by, then how are we supposed to add up the total amount of work that is done as the system is constantly changing? Well, that's starting to sound more and more like a calculus problem. We have a force that varies with respect to some term, and as that force changes, the force does work, but the more the force changes, the more the infinitesimal amount of work changes, and so we're going to have to add up all these infinitesimal little changes until we get a total. And that is just a roundabout way of saying that we need to take an integral. So let's explore what it means to find the work done by a force using the integration approach. And we can actually do this with a constant force, just to give us an idea of what needs to happen. Let's say we have a force of a constant magnitude, we'll say 100 newtons, and we're going to go through a displacement of 20 meters. And let's graph this. Let's graph the displacement in meters versus the force in newtons. So every one of these little tick marks will be 2 meters at a time, and then we'll have 10, 20, 30, all the way up to 100 newtons. This isn't going to be a very impressive graph because our force is constant. All we get is a flat line for that constant force. But what happens if you take that line and you treat it as a function and you add up the area that exists underneath that function? That is the basic definition of integration. You're adding up the area underneath the function or underneath the curve of that graph. This is really easy for us to do because the area underneath this force graph is just a rectangle, and the rectangle has dimensions of 100 by 20, and so we get an area of 2,000. Combining the units of Newton meters, that becomes 2,000 joules. And this is just the work. So we can find the work done by a force by adding up the area that exists underneath the function. Now, as I said, very, very easy, very straightforward if the force is uniform, if it's constant. So let's take a force that's not uniform. Let's take a force that is changing with respect to position. Let's see how we should do this. Let's do a force like, well, I should probably redraw this. I'm not going to get the graph that I want out of this. I'll make the graph a little bit bigger. So displacement in meters, force in newtons. We'll do 5, 10, 15, 20, 20, 25. And these will all be 1, 2, 3, all the way out to 10, 11, 12, 13, 14, 15. So let's say that we have a force that changes with respect to position that looks like this. Now, what we have is, at this point, we have a final value of 25 for the force, and we have a final position value of 15 versus, we'll assume that that's crossing at the 0 point. My graph got kind of sloppy here. But I need to figure out what is the area underneath this curve. It is the area underneath the force function as we change with respect to position that tells us how much work has been done. Well, this is a triangle. We have a height of 25, we have a base of 15, and if you remember from your days back in geometry, the area of a triangle is half the base times the height. So we'll take half of the base times the height. We'll plug that into our calculator. 15 times 25 divided by 2. This comes out to be 187.5. And the area of this particular function, force over displacement, is the work that was done by that force. So this is in joules, 187.5 joules worth of work have been done. But we should be able to assign an equation for this function. There should be an equation that describes the changing rate of the force with respect to the displacement. And for just having a straight line, that equation would be the slope. If we remember, every line can be represented using the point slope form. In this case, y is the vertical axis or the force value. X is the horizontal value, or d. B is the y-intercept, which is occurring down here at 0. So we'll go ahead and let that be 0. We said y was equal to f, x was equal to d, and the only thing that's left is to find the slope. But slope is the measure of rise over run. Rise is the change in the vertical, 25. Run is the change in the horizontal, 15. So 25 over 15, that'll reduce to 5 over 3. And there's the equation. F equals 5/3 d, where d is the horizontal variable. You could just as easily call it x if you want to. And then F is the corresponding force that results from changing our displacement. In fact, I'm going to go ahead and change this to x just because it'll make more sense in the next step that we take. We'll change that to x. We'll change that to x. All right. So why do that? Well, the moment we have a function that we can play with is when we can start doing the calculus. And taking the integral of a function is adding up the area underneath that function. And that's exactly what we need to do. We need this to be a definite integral, so we do need to assign some limits to our integration, but as we integrate our force function with respect to position, that just means that we have to integrate from some initial to final position value. And this is how we're going to find out how much work is done by a variable force. We need to integrate that force with respect to the changing position. Now, I will bring to your attention, this is a force that is changing with respect to position. And the original equation that we had for evaluating force was taking the force times the displacement. That's exactly what we're doing here in the integration. But force could vary with respect to a lot of different variables. This particular equation is only going to be valid if we're using a force that varies with respect to position. If it's a force that varies with respect to time, well, that's not going to work, and I think you can see why. Because then I would be trying to take the integral of some kind of time-dependent function with respect to a variable that is not time. That's not going to work. If we did have a case where the force was changing with respect to time, then we would have to figure out some way of converting that variable dependency. We'd have to figure out a way of converting that function from time dependency to position. But that's a discussion for another day. For now, we just want to focus on getting through this example. For the triangle case, we want to find the amount of work done. We already know what it should be. It should be 187.5. That's our goal, is to reproduce this. The limits will be the starting and ending values on the x-axis. We're going from 0 to 15. And we're integrating our force function. Well, we were able to find that force function. It's 5/3 x, and we have to integrate with respect to x. Here we go. What is the integral of some polynomial statement where a is a constant and n is the power? Well, the constant comes along for the ride. The power increases by 1, and then we have to divide by the new power. So what we're going to get is 5/3. The power has to be increased by 1, so this will become x squared over 2. Or we have 5/6 x squared evaluated from 15 to 0. 5/6 times 15 squared minus 0 will be our answer. And if we've done everything right, this should come out to equal 187.5. 15 squared is 225. If we multiply that by 5, that becomes 1,125. We divide that by 6, and voila. There's our answer, 187.5 joules. So this method does work. This method, surprisingly, also works for the constant forces. Try applying that method to a constant force. How much work is done by this constant force of 100 newtons over a displacement of 20 meters? Well, our equation says integrate your force function. What's the function that describes a constant value? The constant. So we go at 100. And we have to integrate that from initial to final position. And now we can see that this is really just a lot of busy work because we're going to get the same outcome as what we expected. The integral of 100 will become 100x, evaluated from 0 to 20, and that makes 2,000. All right, so this method works for a constant force. This method, sorry, getting tongue-tied there. This method works for a variable force. What if you had a force function that looked something like this, and you wanted to know how much work that force was going to do over the full displacement? Well, you would just find the area underneath the curve. Except, what is the function that describes that curve? Kind of need that. So in a case like this, in order to solve for the work that is being done, this is not something that I'm going to be able to look at and apply, point slope method and figure out what that function is. In a case like this, I would almost definitely have to be given some kind of function relationship so that I could plug this in to an integral, evaluate it between initial and final points. Doesn't even have to be those 2 points. We could find the amount of work done between these 2 points if we wanted. We don't have to use the entire function. We could just find out how much work is done here if we wanted. But this is how we're going to do it. We're going to set up the integral with respective limits. And that means we have a third option for finding the work that is done by a force. If the force is variable, or even if the force is constant, this integration method is still valid. And we can figure out how much work is done by that variable force. What if your force is acting in more than one direction? Well, in that case, then you can add how that force is behaving in those other directions. So if you know how your function is changing with respect to x, then you can find out how much work your function does. If you know how your function is changing with respect to y, then you can find out how much work it does in the y and the z. And because work is a scalar quantity, we can add the expressions together. But I don't have any plans of giving you anything more than a one-dimensional case scenario for work done by a variable force. So we don't need to worry about that for this class. However, moving on to future engineering coursework, you might have to expand this expression into x in xyz, but we can do that if we have to. We're just not going to spend a whole lot of time on that because we do need to move on. But 3 different methods now for finding the work done by a force. And now that we have these 3 different methods, now that we know how to find the work done in a system, we want to take that work and apply it to a change in kinetic energy. All right. Well, we've seen one example of a mass sitting on a flat tabletop. We had an applied force, we had a friction force, there was a normal force, a gravity force. So what we need to do now is just make the problem a bit more difficult. And for that, we're going to take our mass and we'll place it on an inclined plane. We'll start the mass at the top of the inclined plane. We'll consider no friction for the time being. We can reincorporate friction into these problems, but for right now, we just want to see how the work energy theorem relates to the forces and the change in energy We don't need friction to complicate things too much right now, but we want to find the network that is done as this mass slides down the incline and relate that to any change in kinetic energy for that mass. We'll give the mass a value of 10 kilograms. The incline will be 50 degrees. And we'll say that the displacement down the slide has a value of 5 meters. I want to know the amount of work that is done on this mass. So specifically the net work that is done. And then what is the change in the kinetic energy of the block, and how fast is the block going to be moving when it gets to the bottom of the incline if it started from rest at the top. Anytime we have any kind of difference in velocity, we should expect to be able to use change in kinetic energy as a means of solving what's happening in the system. And if there is a change in kinetic energy, then we should also expect there to be some relationship to net work that is done in a system. And if we can go one way with the math, then we should be able to go the other way. Okay, net work. We'll start there. Now, could you do this problem with kinematics? Absolutely, you could. If you want to work this problem with kinematics and then try to match your answers up, that would be a great side exercise. When it comes to a quiz or a test, I would say whatever method you're most comfortable with is what you should use, unless it specifically says that you should use, method A versus method B in solving a problem. But we're going to use the work and kinetic energy approach because this is chapter 7 after all. Net work is the sum of all work done by all forces in the system. So we need to take a moment and identify all of the forces that are going to be acting on this mass as it slides down the incline. The first force of note would be the weight. Weight always points straight down. We have the normal force, which points normal to the surface of contact. And that's it. That looks like the only two forces that are acting on this mass as it slides down the hill. And we've got the displacement vector pointing downhill. Ultimately, the displacement vector will have to be used in evaluating the work done by these different forces. Now, we could set up a reference frame. There's absolutely nothing wrong with setting up a reference frame. And in previous problems that involved inclined planes, we usually had a reference frame that was set up on the incline itself. Now, again, we don't necessarily have to have a reference frame for this problem, and I'll show you why here in just a second. With only having those two forces, we only have these two work expressions that have to be evaluated. The last example problem that we had that involved these two forces, neither one of them did any work. But that had everything to do with the angle relationship between those forces and the displacement vector. So let's take this displacement vector and let's bring it down right here so that we can better compare it to the directions that the normal force and the gravity force are pointing. The normal force is pointing normal to the surface of contact, which is 90 degrees with respect to the displacement vector. If we attempt to evaluate the work done by the normal force, okay, so now you've got your choice of 3 different ways that you can evaluate your work. Well, do you want the magnitude and angle? Do you want the components? Or do you want the integral? Since I already know what the angle is between these 2 vectors, I'm going to go the angle route. Specifically because that angle is 90 degrees, and that's going to give me 0 work. It doesn't even matter what the normal force is or what the displacement is. The angle between those vectors is 90 degrees. The normal force does not do any work. Gravity. How much work is the gravity force going to do? Well, we have mg. We have to dot that with the displacement vector. I think I'll try the magnitude and angle approach for these. Now, looking at the diagram, gravity is pointing straight down. Displacement vector is pointing along the incline itself. The angle that I need is right here. That angle is not 90 degrees, but it's also not 0. What is it? And just so we don't get ourselves confused, I'm going to call this phi instead of theta, because I'm using theta as the angle of the incline. And until we know for sure if they're the same or different, let's just separate the 2. But if we remember back with our previous problems where we dealt with inclined planes, a lot of times we took the gravity force and we broke it up into components that pointed parallel and perpendicular to the incline. And the angle of our incline, theta, always ended up in this top corner there. Well, if this is theta, and there's a 90-degree angle between the perpendicular component of our weight and the downhill direction, which is where D is pointing. Well, if that's all 90, that means that phi has to be the difference between 90 and theta. Okay. Theta was measured as 50 degrees, so that means that phi is 40 degrees, and phi is the angle that exists between those 2 vectors. Now, did I necessarily need the reference frame to make all of those conclusions? And the answer is no. It was nice to have the reference frame there to kind of coach me along in breaking up those components of the weight, but I didn't necessarily have to have that reference frame there. All right, so phi is the 40 degrees. Need to figure out what cosine 40 is. The mass was 10. The displacement was 5, so we've got 10, 9.8, displacement was 5, we've got cosine of 40. Back to our calculator. Cosine of 40 times 10 and 5 is 50, times 9.8 makes for 376 joules worth of work. The net work is the combination of work done by the normal force, 0, plus work done by gravity, 376. Now that we have the net work, we can relate the net work to a change in kinetic energy. Change in kinetic energy, final minus initial. Final kinetic energy is based off of the final speed of the mass. Initial kinetic energy is based off the initial speed of the mass. We said our mass started with an initial velocity of 0, so that means we have an initial kinetic energy of 0. As such, the final kinetic energy of the mass has to equal the work that was done. The work was positive, so we should see an increase in the speed of the block as it slides down the incline. That makes perfect sense. We solve for the final speed. Again, I'm using the word speed because the best that we can do in going backwards in the math here is to get the magnitude of the velocity. But we should know with pretty good certainty that the final velocity is going to be in the downhill direction. So if we had to assign a direction to that, it would be positive. Okay, solving for V final, we need the 376, which was the work, multiply by 2, divide by the mass, which was 10. And then square root everything. And I am getting 8.67 meters per second for the final velocity. Okay. Well, let's change it up just a little bit. Just a little bit. Let's say that this block actually started with a downhill velocity of 5 meters per second. What would be the final velocity when it gets to the bottom of the hill now? Now, it might look like we have to start over, but let's just go through these steps again real quick. Mass, angle, displacement are all the same. Net work will be responsible for the change in kinetic energy. We still only have two forces involved, normal and weight. The normal force is still not going to contribute any work. The gravity force is still operating over the same displacement with the same angle. So gravity is still providing the same amount of work, 376. That 376 joules is responsible for changing the kinetic energy of the system. The only difference that we have now is in the second to last line. We have an initial velocity that is no longer 0. And so we will have to make a slight alteration in how we solve for the final velocity. We have 376 for the net work. I'm going to add the initial kinetic energy term over to the other side. We're solving for the final velocity. So that means I need to multiply everything by 2, divide everything by the mass, and then take a square root. And that'll be our final velocity. So 2 over mass is 10. 376 plus 2 mass And we said the initial velocity was going to be 5 squared. So let's see what we get. 376 times 2 over 10 is 75.2 plus. Now here I have half of 10, but that's being multiplied by 2 over 10. So all of that's going to cancel out, and I'm just going to be left with 5 squared, which is 25. Add that to the 75.2, and I'm getting 100.2. Square root of that is, I'm just going to round that off to 10. So by having that extra amount of kinetic energy at the beginning of the problem means that we're going to have a final velocity that is higher. Even though the same amount of net work was done, we started with a higher amount of kinetic energy. We added to that, and we got a final kinetic energy that was larger as a result. Okay, there are more examples that can be done with this material. We could incorporate tension forces. We can incorporate friction forces. We can incorporate centripetal forces, see how much work is done by those. There's a lot of different forces out there that can do work, and any force that does work has the potential of changing the kinetic energy of that object. We'll look at one more quick example problem, then we'll end this video. When we come back for the fourth video, we will look at even more examples, but we're specifically going to focus on a variable force that is related to springs. And these spring forces can be equated to other systems with elasticity, like a rubber band or a bungee cord. We can use similar expressions for those, but those are variable forces, and that means we're going to have to use the calculus approach to solving the work that is being done by those spring forces, since they're variable. Okay. This last example that I want to do, I just want to drop a rock off the ground, or from a cliff down to the ground. So we've seen this problem multiple times already. We'll start up here with 0 initial velocity. I'm going to drop the rock. So we have mg as a force that is working in the direction of the displacement. So, how much work is required to get the rock from the top of the cliff down to the ground? And we'll assume that the full displacement is d. All right, work done by gravity is mg dot d. We need the magnitude of each times the cosine of the angle between them. So we'll assume we know the mass of this rock. You can give it any mass that you want, really. And we'll assume we know the height of this cliff. What I want to do is just get a general solution for this right now. You can come back and plug whatever numbers in that you want. But the angle relationship between these two vectors, they're both pointing down. So there's an angle relationship of 0. Cosine of 0 evaluates to 1. And all I get for the work done by our gravity force is mgd. And it's positive. This positive work means that we're going to be putting energy into the kinetic energy of this rock. So how fast is the rock going to be traveling when it gets down to the ground? If gravity is the only force, then by default, it is the net work that is contributing to the change in the kinetic energy of the rock. Because the rock was dropped from rest, initial kinetic energy is 0, which means the final kinetic energy is equal to the work done by gravity. Oh, but look at this. We've got the same mass on both sides of the expression. That mass is going to cancel out. And the final velocity when we impact the ground should be square root of 2gd. That final velocity is independent of the mass. If we think back to our days in Chapter 2 and Chapter 4, could we have solved for the final velocity using just kinematics? And the answer is yes. The reason why we're able to use kinematics is because the mass becomes irrelevant in this problem. It shouldn't matter if I have a small pebble or a rock or a boulder. Every one of them should be accelerating at the same rate of g over the same displacement. They should all experience the same change in velocity. And that's exactly what the kinematics says. But that's also what our work energy theorem says, which is kind of nice. We want different approaches to solving these problems to result in the same outcome. So what would happen if, let's say we want to reproduce this experiment. Well, if we want to reproduce it, we have to take the rock, we have to pick it up, we have to bring it back to the top of the cliff. Okay, let's do that. We're going to pick up the rock, we have to displace it back to the top of the cliff. But as we do that, how much work is gravity doing as we try to move the rock back up to the top of the cliff? Well, now gravity is going to be doing work in the amount of negative mgd. The reason it's negative is because our vectors are pointing in opposite directions. We have an angle relationship of 180 degrees. And we end up getting a negative work. When we fall, gravity helps us to fall. Hence the reason we're putting energy into the rock. But if we try to move up, gravity's not going to help us move up. Gravity's going to resist or work against us. And that's where the minus sign on this comes from. In the next chapter, Chapter 8, this idea is going to become kind of important because we started up here. We dropped the ball or the rock, whatever it happens to be, and then we picked it up and we brought it back up to the original starting point. This is what we call a closed path. We started and ended at the same location. How much net work was done by gravity as we traveled over that closed path? Well, this was the amount of work that gravity did as the rock fell down. This was the amount of work that was done by gravity as the rock was brought back up. Combining those two works, this was up, this was down. Well, we're getting a net work of 0. This is not to say that gravity didn't do any work. It's just saying that all of the work that was done by gravity throughout the entire journey ended up being 0. And we have a term for forces like this. We say forces that do network of 0 over a closed path are called conservative forces. So what this means is that the gravity force is conserving the amount of energy that is transferred into or out of the rock as it moves about that closed path. Now we can look at other types of forces and we can ask, are they conservative, or what would be the alternative to being a conservative force? Well, there are such things as non-conservative forces. And these are going to be forces that do not do network of 0. So over here, conservative forces will have network of 0 over a closed path. Non-conservative forces will not do network of 0. In fact, non-conservative forces will actually do negative network. An example of a non-conservative force would be friction. A really easy way of showing that would be to take a block, allow friction to act on it. In this case, it would have to be kinetic friction because you move. If you allow friction to work over that displacement, now, regardless of the displacement or the magnitude of the friction force, the angle relationship between the vectors is 180 degrees. That cosine 180 results in a minus, and so negative work is done as that box slides to the right. Now, bring the box back. Okay, we have to have a closed path. We'll let the box come over here, but then we have to bring it back. If you bring the box back, friction points in the direction opposite of the displacement. If we evaluate the work, well, we're still going to get a cosine 180 relationship between those two vectors, and we get a minus FKD as we bring that box back to the left. So during that closed path, we have work done in the amount of minus FKD plus a minus FKD, which is a minus 2 FKD. And that is not 0. During this closed path, friction took energy away as we moved to the right, and then it took more energy away as we moved to the left. For any object that moves, friction will only take energy away. Friction will never give that energy back, at least not in a usable form. But we'll talk about the effects of friction and energy and work some more in the next chapter. But this fourth video, we're going to exclusively devote to springs, and then we'll look at some examples that involve springs and maybe some other forces that we haven't quite seen in any of these work energy theorem problems yet. All right, so we'll see you at video 4.